In physical cosmology and astronomy, dark energy is an unknown form of energy that affects the universe on the largest scales. Its primary effect is to drive the accelerating expansion of the universe. Assuming that the lambda-CDM model of cosmology is correct, dark energy is the dominant component of the universe, contributing 68% of the total energy in the present-day observable universe, while dark matter contributes 26% and ordinary, baryonic, matter contributes 5%, and other components such as neutrinos and photons account for less than 1%. Dark energy's density is very low, much less than the density of ordinary matter or dark matter within galaxies. However, it dominates the universe's mass-energy content because it is uniform across space, so as the universe expands, there will be more and more dark energy. The first observational evidence for dark energy's existence came from measurements of supernovae. Type 1a supernovae have constant luminosity, which means they can be used to measure distance accurately. Comparing this distance to the redshift, which measures the speed at which the supernova is receding, shows that the universe's expansion is accelerating. Before this observation, scientists believed the gravitational attraction of matter and energy in the universe would cause the universe's expansion to slow over time. Since the discovery of accelerating expansion, several independent lines of evidence have been discovered that support the existence of dark energy. The exact nature of dark energy is still a mystery, and explanations are plenty. The main ones are a cosmological constant, representing a constant energy density filling space evenly, and scalar fields, dynamic quantities having energy densities that vary in time and space. A cosmological constant would remain constant across time and space, while scalar fields can vary. The nature of dark energy is more hypothetical than that of dark matter, and many things about it remain speculative. Dark energy is thought to be spread very evenly throughout space, and not dense, and is not known to interact through any of the fundamental forces other than gravity. The reason dark energy can have such a profound effect on the universe, making up 68% of universal density in spite of being so diluted, is that it is believed to uniformly fill otherwise empty space. The vacuum energy, that is, the particle-antiparticle pairs generated and mutually annihilated in accordance with Heisenberg's uncertainty principle, has been often invoked as the main contribution to dark energy. The mass-energy equivalence postulated by general relativity implies that the vacuum energy should exert a gravitational force. Hence, the vacuum energy is expected to contribute to the cosmological constant, which in turn impinges on the accelerated expansion of the universe. However, the cosmological constant problem asserts that there is a huge disagreement between the observed values of vacuum energy density and the theoretical large value of zero-point energy obtained by quantum field theory, so the problem remains unresolved. Independently of its actual nature, dark energy would need to have a strong negative pressure to explain the observed acceleration of the expansion of the universe. According to general relativity, the pressure within a substance contributes to its gravitational attraction for other objects just as its mass density does. This happens because the physical quantity that causes matter to generate gravitational effects is the stress-energy tensor, which contains both the energy, or matter, density of a substance and its pressure. In the Friedmann-Lemaitre-Robertson-Walker metric, it can be shown that a strong constant negative pressure or tension in all the universe causes an acceleration in the expansion if the universe is already expanding, or a deceleration in contraction if the universe is already contracting. This accelerating expansion effect is sometimes labeled gravitational repulsion. In standard cosmology, there are three components of the universe: matter, radiation, and dark energy. Matter is anything whose energy density scales with the inverse cube of the scale factor, while radiation is anything which scales to the inverse fourth power of the scale factor. The final component is dark energy, which is an intrinsic property of space and has a constant energy density, regardless of the dimensions of the volume under consideration. Thus, unlike ordinary matter, it is not diluted by the expansion of space. The evidence for dark energy is indirect but comes from three independent sources: distance measurements of supernovae and their relation to redshift, which suggest the universe has expanded more in the latter half of its life. The existence of dark energy, in whatever form, is needed to reconcile the measured geometry of space with the total amount of matter in the universe. Measurements of cosmic microwave background anisotropies indicate that the universe is close to flat. For the shape of the universe to be flat, the mass-energy density of the universe must be equal to the critical density. The total amount of matter in the universe, including baryons and dark matter, as measured from the cosmic microwave background radiation, accounts for only about 30% of the critical density. This implies the existence of an additional form of energy to account for the remaining 70%. Measurements of large-scale wave patterns of mass density in the universe also suggests that the density of matter in the universe is only 30% of the critical density. A 2011 survey, the Wiggle-Z Galaxy Survey of more than 200,000 galaxies, provided further evidence towards the existence of dark energy. Thus it seems that dark energy will remain a part of science for the foreseeable future, as no other theories can defeat it.